Okay, so recently Elon Musk tweeted about Tesla's AI, whereby he mentioned that even some of the best AI software engineers in the world don't realize how advanced Tesla AI has become. Now, as much as some people might want to test the truth in this statement, it might actually be true. We've witnessed Tesla's massive growth over the past years, and while most people have focused on the production, deliveries, and returns, nobody really pays much attention to the automaker's AI software and its development over the years. Well, let's have a look at it. But for starters, let's quickly highlight Tesla's Starlink project. Now, SpaceX founder and CEO Elon Musk said that his company is now focusing on cyber defense and overcoming signal jamming of its Starlink internet satellites amidst Russia's ongoing invasion of Ukraine. Musk and SpaceX sent Starlink terminals to Ukraine at the request of a government official after internet service was disrupted across the country by the Russian invasion. A shipment of Starlink ground terminals, which use an antenna and terminal to access the satellite broadband service, arrived in Ukraine by February 28th. With the terminals in use, Musk said that SpaceX is working to keep them online. So, with the Starlink project already in use, coupled up with Tesla's awesome AI software, what would stop Tesla from dominating the world? Now, a couple of days ago was the first Tesla AI Day, where Andrej Karpathy, the director of AI at Tesla, and others presented how Tesla's autopilot works from the image acquisition through their 8 cameras to the navigation process on the roads. Tesla's cars have 8 cameras which allow the vehicle to see their surroundings and far in front. Unfortunately, you can't simply take all that information from these 8 cameras and send it directly into an AI that will tell you what to do, as this would be just way too much information to process at once, and the Tesla computers aren't that powerful yet. Well, try to imagine a situation whereby you have to process a lot of information at once. Of course, it's just as difficult for humans as it is for computers. So basically, it's the same for computing devices like COUs and GPUs. With that said, how then do the cameras manage to process the information? So what happens is that this data is compressed while keeping the most relevant information similar to what our brain does with the information coming from our eyes. To do this, Tesla transfers the data from the 8 cameras into a smaller space they call the much smaller vector space. If you're wondering what we're talking about, this space is a three-dimensional space that contains all the relevant information in the world like the road signs, cars, people, lines, among other things. This new space is then used for many different tasks that the car will have to do, like object detection, traffic light tasks, and lane prediction. But how do they go from 8 cameras, which would mean 8 times three-dimension inputs composed of red, green, and blue images, to a single output in 3 dimensions? Now, this is achieved in 4 steps and done in parallel for all 8 cameras, making it super efficient. At first, the images are sent into a rectification module, which takes the images and calibrates them by translating them into a virtual representation. This step dramatically improves the autopilot's performance because it makes the images look more similar to each other when nothing is happening. And that allows the network to compare the images more easily and focus on essential components that aren't part of the typical background. So you're probably wondering what happens next after that. The new versions of the images are sent into a first network called RegNet. This RegNet is just an optimized version of the convolution neural network architecture CNNs. Basically, it takes these newly made images, compresses the information iteratively like a pyramid where the start of the network is composed of a few neurons representing some variations of the images, focusing on specific objects, telling us where it is spatially. The deeper we get, the smaller these images will be, but they will represent the overall images while also focusing on specific objects. So at the end of this pyramid, you'll end up with many neurons, each telling you general information about the overall picture, whether it contains a car, a road sign, or other important things. So in order to have the best of both worlds, information is extracted at multiple levels of this pyramid, which can also be seen as image representations of different scales, focusing on specific features in the original image. You'll end up with local and general information, all of them telling you what the images are composed of and where. Then this information is sent into a model called BiFPN, which will force this information from different scales to talk together and extract the most valuable knowledge among the general and specific information it contains. The output of this BiFPN network will be the most interesting and useful information from all these different scales of the 8 cameras. So it contains both the general information about the images, which is what it contains, and the specific information, such as where it is and what size. So now you have the most useful information coming from different scales for all 8 cameras. You need to compress this information so that you don't have 8 different data inputs, and this is done using a transformer block. In a nutshell, this block will take the 8 different pictures' condensed information and transfer it into the three-dimensional space you want, basically the vector space. It'll take this general and spatial information called the key, calculate the query, which is of the dimension of the vector field, and try to find out what goes where. For instance, one of these queries could be seen as a pixel of the resulting vector space looking for a specific part of the car in front of you. The value would merge both of these accordingly, telling you what is where in this new vector space. This transformer can be seen as the bridge between the 8 cameras and this new 3D space to understand all interrelations between the cameras. Now that you've finally condensed your data into a 3D representation, you can start the real work. This is the space where they annotate the data they use for training their navigation network, as this space is much less complex than 8 cameras and easier to annotate. Okay, so you have an efficient way of representing all your 8 cameras now, but you still have a problem, which is single camera inputs are not intelligent. If a car on the opposite side is occluded by another car, you need the autopilot to know it's still there and it hasn't disappeared because another car went in front of it for a second. To fix this, you have to use time information, or in other words, use multiple frames, which are a feature queue and a video module. The feature queue will take a few frames and save them in the cache. Then for every meter the car does, or every 27 milliseconds, it'll send the cached frames to the model. Here they use both a time or a distance measure to cover when the car is moving and stopped. Then these 3D representations of the frames you just processed are merged with their corresponding positions and kinematic data containing the car's acceleration and velocity, informing you how it's moving at each frame. All this precious information is then sent into the video module. This video module uses these to understand the car itself and its environment in the present and past few frames. This understanding process is made using a recurrent neural network that processes all this information iteratively over all frames to understand the context better and finally build this well-defined map that you see. Now, since it uses past frames, the network now has much more information to understand better what's happening, which will be necessary for temporary obstructions. And this is just a simple explanation of how the Tesla AI software works. Well, just like we said, many people don't know about how this works. But as always, we've got you. If you enjoyed the video, remember to like, share, and subscribe. We hope to see you next time. Stay safe.